You welcome to another episode of Black Guy Does Physics, where even though there's some bass in the back, I'm gonna try and stay focused, man. Alright. If you want some help with your AP physics, AP mechanics, math problems, all that good stuff, drop a like, comment, all that stuff in the back, and just like the bass goes, smash that button. Smash that subscribe button. Nah, son. Not because I'm a black guy, I don't rap. Wrong black guy, dude. Alright, keep it moving. With that being said, let's get it cracking. Alright, today we're about to be looking at AP Physics 1 2021, number 2, which is one of them lab things, son. And from my experience right now, all them kids freak out about this lab. Why? It's because, no cap, it's kind of stupid. That's why it is. It's kind of stupid. Why? Because it's a long, look at all this junk. So much reading and all that. But what they're doing is that they're actually trying to test your understanding of the information that you're presenting. That you're presenting and that you're presented with. You see what I'm saying? If you could relate your conceptual things to experimental things to your equations. Remember, the concepts are born from the equations are born from the concepts. So that means that the concepts and the equations are genetically aligned. And then the experiments are what is then used to prove those things. So they're all the same thing. So from my perspective, all I do is that I try to use some equations and try and figure stuff out as I go along, right? So I see a rod here. That's the first thing you want to do. Look at your diagram. I don't know what the hell is happening. I see a rod with two hooks, man. It is what it is. So I don't spend too long thinking about that. I just keep it moving and start reading. A group of students investigating how thickness of a plastic rod affects the maximum force at which the rod can be pulled without breaking. Oh, so they're going to pull this rod. Two students are discussing models representing how F max depends on the rod thickness. Student A. Now, with these student A and these student B claims distinction, you want to make sure that you look at exactly what they're trying to say. Because what they're trying to say might be correct or it might be wrong. And they have this way in AP Physics 1 where they're going to try and test you on, oh, do you agree with what they said? And why do you agree? That's how I teach my class, really. But lots of students get confused with that. So let's see here. Claims that F max is directly proportional to the radius of the rod. What does that mean? That means that as F max goes up, the R goes up. Or as R goes up, F max goes up. If R goes down, F max goes down by the same amount. By the same amount. It's a 1-to-1 ratio. That's what directly proportional means. 1-to-1. I should do a video on graphs and like what directly proportional mean and those types of graphs. I should. Student B claims that F max is directly proportional to the cross-sectional area of the rod. That means that it's a 1-to-1 to the area. So the area, it would be, if the area goes up, then F max, it's a 1-to-1. But what affects the area? What's area? Pi r squared, I think. Yeah. Pi r squared is the area. So in essence, what you're looking at is that if you look at the force to the radius for the second student, it's not a 1-to-1 anymore. It's a 1-to-squared. That's a good trick right there. I see what they're trying to do, AP. Let me say that again. The area is pi r squared, right? Pi is a constant. R is the thing that is there. R could be changing. So what you could see is that because it's pi r squared, if you're looking at F to R for the second one, it's not a 1-to-1 ratio. It's a 1-to-squared ratio. You should see how I'm doing my hands like you could see me. I should get a video so you could see me. Brilliant. The area of the base of the cylinder shaded gray in the figure above. Okay, cool. The students have collection of many rods of the same material. The rods are of the same length but come in a range of 6 different thicknesses. Design an experimental procedure to determine which student's model is either correct and how F max depends on it. Every single one of these lab things, they're going to give you this junk. Below is a table. List the quantities that you could measure, symbol of the measurement and the equipment. Then they're going to ask you this. Describe the overall procedure to be used referring to the table. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty as needed. Use the symbols defined in the table and or including a simple diagram or setup. That's what they're going to say. So what I've seen with the students is that they start doing this junk first and start getting confused as hell, right? In this particular case, in all of them, you don't want to start with this first. You want to actually set the lab up in your head and write that junk down. You want to try and set your lab up. In most cases, what you'll have is that you could use a formula, an equation that deals with the concepts that you're dealing with, and use that to say, okay, what do I need to measure? What are the things that I need to measure from this thing, right? In this case, there's no straight up formula that is here that you need to get from whatever. But you could see the thing that you're testing, I need black, the thing that you're testing is that you're testing one, F is proportional to R, and one is F is proportional to A, which we already said that would be F is proportional to pi R squared. So the question is now, what from this can you measure? The things that you could measure are F, which is a force, and R, which is the radius. So now all you have to do is like, okay, if I need to measure F and R, what are the things I need to use to measure F and R? Well, F is a force sensor. School has a force sensor. Cool. Force sensor. Boom. R, I need R. I could use a ruler, but if you want to be fancy pants, you could use a caliper, right? A caliper is good for round things if you want to figure out R. So now once you know that, okay, I have to measure F and I have to measure R, you could write that junk here, right? Then you could, if you want, you then set up the thing in your head. You're like, yo, what am I going to do? What am I going to do? So obviously you'd have to, you're going to have to measure the radius of the thing. So measure radius, R, you need to measure that, right? To see how the radius of the thing is. And then what you're going to do, you're going to apply force with two force sensors at each end. So you're going to have apply force. And you're going to stretch this thing until it breaks or whatever it needs to do, right? And then record that. And you're going to record, right? Record it. So you're going to measure R, record that. Then you're going to measure the force as you attach the force sensor to the thing, and you're going to stretch it one end, and I think I said two ends before, but just one end. Hope you hear that bass in the background. That's not me, people. That's outside. Hey, I need a padded room to do this in. This is atrocious. But anyway, so you pull it, and then once you get the reading at which it breaks, you record that. So what do? You always do this. You get the same size rod, and you repeat this thing multiple times. So all you have to do is just repeat it multiple times. Yeah, you repeat it multiple times to reduce uncertainty. So you repeat that same size rod multiple times. Boom. Once you repeat that multiple times, boom, then you go get other rods, right? You get other rods of different sizes and repeat what you've just done. That's the basic setup. There you go. Once you have the data points, what do you usually do with data points? You're going to say, okay, then what you're going to do is that you're going to plot the data points. In this particular case, if you want to plot F versus R, you could put F versus R, or you could plot F versus R squared. But if you plot F versus R squared, you should get some linear relationship or whatnot. But you're going to want to put F versus R because you want to see the relationship between F and R. Okay? And that's what you do. Cool. Part B. For a rod of radius R0, it is determined that F max is F0 as indicated by the dot on the grid. On the grid, draw and label graphs corresponding to the two students' models for the dependence of F max. Clearly label graph A and B corresponding to the appropriate model. So for A, remember I said that it's, so if I'm plotting F versus R, then if this is true, if this one is true, then what I'm going to end up with is, let me put a red, I should be ended up with a straight line because those things are directly proportional to each other. So you have one straight line. and it would have to go through that point because that's your original point. Now, if I go and I say that I'm plotting f is proportional to pi r squared, and if I plot f versus r now, this is not a 1-to-1. This is a 1 to squared. So whenever you plot a 1 to squared, your crap looks like, not your actual crap, but you look like a quadratic thing, like a parabolic, because it's quadratic relationship between them. That was relatively easy. Thank you, AP. I appreciate it. Usually these questions are like stupid. Oh, you gotta put A and B. Yeah, forgot about that. The table below shows the results of measurements taken by another group of students for rods of different thicknesses. So they give you all this on the grid. Pardon me. Once you see this stuff, that simply means that once you see a table, this is from my AP Mech students too. Once you see a table, you already know you're gonna have to graph, man. It's ridiculous, but it is what it is. So they're gonna graph this, and for graphing, you have to. In this case, they tell you what you have to do. You have to scale, always scale, and you have to label your axis always. By scaling, it means you want this as large as possible, and you always have to put units, correct units. These are the three things that you have to do on every graph to get full points. You have to scale properly, not property, scale properly to make this thing as large as possible, and you have to label your axis correctly, like what goes on what and what goes on what, and then you have to include the proper units. So I think for this, let's see if I could scale this. The radius, so I'm gonna have to have force, so it's F. What's the units? You put the proper units. They already told you here, newtons, and we're gonna put R, which is the radius. You could just write R, I think, and that's in millimeters. Oh, they put rod radius, right? And now you're gonna try and scale this out. So if you try and scale this out, this is 0.5, 1, 2, 2, 4, 5. 1, 2, 1, 2, 3, 4, 5. Oh, that makes it easy. So this would be 0 0.5, 1, 1.5, 2, 2.5, D. And then 40, oh crap. This goes all the way to 900, and this is 1, 2, 3, 4, 5. Oh, you can make that 1,000. Yeah, man. That should be like 200, 400, 600, 800, 1,000. See? So now your graph is taking up the whole thing, and then you just plot. Hopefully I can plot this chunk. So this is what? If this is, what is this? 40. So 40 would, five of these, so 5 into 200 is 40. So there, this is 120, so that would be 3 of these. 1, 2, 3. I think it's here, yeah. 320, I can't do math, man. That's too much work. I think it should be like here. What's that? 5, 6, 7, 8. 8 fours, that's 320. 520, I don't know what that is. Bruh, why are you 520? Oh yeah, it should be 520. I can't be there. It should be somewhere here. Oh, yeah, 520. Has to be here. And 2.5 is 900. Okay, so 900 is somewhere in the middle here. Yeah, 900. So obviously that's not a straight line, people. It's gonna have to be something like this. Whoa, that's one shot. Cool. That's not a straight line. Which student's model is more closely, that now becomes cake. It has to be model B. Right? Explain your reasoning. Simple reasoning. It's a freaking, what's that thing called? Curve. It's curved. It looks like a parabolic curve. If it was F versus R, then the line would be straight or linear. And that's it. Wow. I thought that would be ridiculously hard, but it turned out it was like not too hard. Usually they are kind of nasty. But you know, kids, I'm glad we did it so we could see that. I'll try and do another one and see what happens. And remember, kids, one thing you should always remember when you're doing these problems, don't be a moo-moo.